we are going to learn an important factor. That factor is called the resistance. The resistance of a conductor is the opposition offered by the conductor to the flow of electric current through it. Normally we are also not, we don't like the changes. Similarly, the conductor also don't like any type of changes. But when the current is passing through the conductor, so what happens, it's the electric field inside that conductor will be changing. That means it is increasing. So that increase in the electric field, that is normally opposed by that conductor, and that opposition is called the resistance. We have the current equation. So this is a basic equation, that is current is equal to NEAVD, and we are going to substitute the value for VD, that is VD is equal to E into, this is a substitution, VD equal to E into E divided by M into T. So by substituting this, we can get I equal to NE square A into T by M into V by I. Again, V by I equal to M into L divided by NE square A into T, where this L represents the length of the conductor and A is the area of the conductor. N we know, N is the number of charge carriers, E is the basic unit of charge, and finally we come to know that R is equal to M by NE square T into L by A, and we know this value is a constant because M is the mass of electron, that is we know that its value is a constant, that is 9.1 into 10 raised to minus 31 kilogram, and E is the basic unit of charge, we know 1.6 into 10 raised to minus 19 coulomb, and N is the number of charge carriers, that is also constant, and T is the time, that is also constant, and the only thing is L and E, where L and A are variable that depends on the conductor. Therefore, we can come at this point, that is R equal to rho L by A, where rho is a constant, and that constant is called the resistivity, or it is known as the specific resistance of the conductor. The resistance, normally it is directly, so from this expression we come to know that the resistance is directly proportional to the length and resistance is inversely proportional to A, and this is known as the laws of resistance, that is R is proportional to L and R is inversely proportional to A. The resistivity, I told you resistivity is this one, and also resistivity, what is the unit of R? R, resistance, the unit of resistance is ohm, and the unit of resistivity, from this expression we can write like this, that is R equal to rho L by A. Similarly, rho equal to R into A by L. That means the unit for, what is the unit for rho? That is ohm into that is meter square by meter for the length, so these two cancel. Finally, ohm meter is the unit for rho. Ohm meter is the unit for rho. Okay, ohm meter is the unit for rho. Rho means the specific resistance or the resistivity of the material. Okay, again, the resistivity depends upon the nature of material and not on the geometrical dimension of the conductor. Okay, so the resistivity is constant for the material. It does not depend on the length or area or any dimension of the conductor. Okay, now, so we have an example, that is, now you consider this is a length and area. We know that the resistance will be equal to the resistance. Suppose you consider the resistance is R. Again, if we increase the length of the material, then what happens? The resistance also becomes double of the previous value. Similarly, here we are sandwiching two resistive materials, and whose area is A by 2 and A by 2. Finally, we know that the entire value of A will be A itself. I mean A by 2 plus A by 2 will be equal to A itself. Therefore, there is no change in the resistance. Okay, now we are going to learn some important relations between um, drift velocity, specific resistance, current, electric field, and voltage. The first relations gives the relationship between resistivity. Thus, this is specific resistance or resistivity. Resistivity is equal to E by J. We know what is J? J is the current density. That is equal to E by NEVD. So this is the equation for, so this is a relation between the drift velocity and the resistivity. That is, resistivity is equal to E by NEVD. Similarly, VD equal to E divided by NE rho. So from this expression, we can rearranging the variables. Finally, we get VD equal to E by NEP. Not P, it is rho. NE rho. NE rho. Rho means the specific resistance or the resistivity. Similarly, VD is equal to V by NE rho into L. VD equal to V by NE rho into I, where I is called the current through the conductor. Since we know that E is equal to V by I, so we can replace this value. We get VD equal to V by NE rho L. Now, some important terms like conductance and conductivity. Conductance is the reciprocal of resistance. So the reciprocal of resistance is known as the conductance, and therefore its unit is also like 1 by ohm. 1 by ohm is also known as mho, MHO, mho. Okay, so the SI unit of conductance is mho. Conductivity is the reciprocal of resistivity. Also, the SI unit of conductivity is mho by meter. Now, the temperature, that means the resistance of the circuit or the conductor will depend on the temperature of the system or the material. The temperature, that is, the basic equation is R equal to M divided by Ne square T into L by A. So when the temperature increases, what happens? When the temperature increases, the number of collisions increases due to more internal energy and relaxation time decreases. When the relaxation time decreases, what happens to the resistance? The resistance increases. So what does it mean? That means when the temperature increases, the resistance also increases. That when the temperature increases, the resistance also increases. So this is the equation. So normally we don't need the derivation for this equation. We just have to remember this equation, that is the alpha, that is the temperature coefficient of resistance, that is alpha is equal to RT by R0 by RT minus R0 by R0 into T. Also we can write alpha equal to R2 minus R1 by R1 R2 R1 T2 minus R2 T1, where R0 is the resistance at 0 degrees Celsius, RT is the resistance at T degrees Celsius. Similarly, R1 is the resistance at T1 degrees Celsius and R2 is the resistance at T2 degrees Celsius. Normally, so from this expression it is clear that R2 is less than R1, then alpha is the temperature coefficient of resistance will be negative. So alpha may be positive, or it may be negative, or it may be 0. If R2 is greater, what is R2? R2 is the resistance at T2 degrees Celsius, right? So when the R2 is greater than R1, then alpha is positive. Okay, then those materials are known as positive temperature coefficient materials. For example, all metals are positive temperature coefficient materials, because when the temperature increases, the resistance also increases for the normal metals. But in the case of, in some other cases, that is when R2 is less than R1, then alpha is negative. So this is also possible, because for some materials like semiconductors like silicon, germanium, or the alloys of these two, say gallium arsenide and gallium indium phosphide. So these material, in this type of materials, when the temperature increases, resistance decreases because of the um, because of some actions that we will discuss later. So in that case, those materials are known as negative temperature coefficient materials. So the examples are silicon, germanium, and all semiconducting conductor materials. In some cases, R2 will be equal to R1. What does it mean? R2 equal to R1. That means even the temperature increases or decreases. That means even the temperature changes will not affect the resistance. The resistance remains the same. So those materials having the zero temperature coefficient materials. For example, manganese constantine. These two materials are the examples for the zero temperature coefficient materials.